Okay, very
All
good.
set.
So it's recording. I would give
Okay.
the floor to you. Good luck.
Excellent. Thank you so much. This group is really amazing, and I'm very honored to be here to present for the First Journal Club. So as mentioned, the paper we're going to be talking about today is Common Critiques and Recommendations for Studies in Neurology Using Machine Learning Methods. Before I get going, I really want to say a big thank you to my co-authors, Wesley Kerr and Andre Ziegler. We really had a very collaborative working for this paper. We all have pretty strong opinions about statistics and machine learning, so it was a lot of fun working with them to come up with the ideas for this paper. And as mentioned, my background is in mathematics, and I kind of slowly became more applied in my interests. So I started with math and then got my master's in statistics, and that really focused on statistical theory. I got my PhD in biostatistics, where then I started working with some machine learning methods. So the framing of my talk is kind of from more of a statistician background than like a computer science or engineering flair. And I think you'll see that in a lot of the topics and themes throughout this talk. All right, so I wanted to start with some of the rationale for this paper. So Wes, Andreas, and I are all editorial board members within the statistical methods portfolio for neurology journals. So we all review about 8 to 12 papers per year, mostly focused on machine learning, although there's some other types of studies that kind of we just get thrown at too. And as we've reviewed, we kind of noticed some common themes that were arising. And so to kind of try to preemptively take an approach to try to prevent some of these issues, we wanted to write this paper with some of the problems that we were commonly seeing and then our recommendations for addressing them. So our paper is a listing of problems that we noticed in some of these machine learning papers. We try to provide examples without calling out specific papers. So it's a lot of systematic reviews and meta-analyses that we include in the paper. We also have recommendations for addressing the issues. And again, I want to highlight this is just written by 3 people who really got tired of typing out the same critiques over and over again in our reviews of papers. So what this paper is not, it's not comprehensive, it's not a checklist or a guideline, it's not a systematic review. We did not do participant study surveys of experts. Like, this is just the 3 of us who got together and noted these common things. So, I think that's an important aspect to highlight, is that it is, to some extent, a little bit, I don't want to say like opinion based, but, a lot of these topics, it's not like set in stone exactly what you should be doing. So some of it kind of is our guidance and our opinion, but also that's based on our experience as, 3 reviewers and researchers in this area. The paper focuses on machine learning, and we very intentionally didn't include anything about AI. We wrote this paper in early 2024, and then it came out, I think, in the online version later in 2024. So as many of you know, machine learning, is pretty established by then, whereas a lot of these AI methods are still very emerging, especially with large language models. And there's a lot of unique challenges and recommendations that I think at this point are somewhat unclear, because there's so many emerging methods, and it's just so rapidly changing. And so most all of the topics in this machine learning talk should be relevant for AI studies, but we didn't want to, say that it's, applicable everywhere, because it's just still so emerging. And I think this is a topic for future work and recommendations. Okay, so I'll get to the introduction now. As you all know, there's been a rapid growth of machine learning in all sorts of medical fields. Neurology, I think we see this big boom, especially because of some of the big data aspects like neuroimaging studies that, have a just huge amount of data that we can use to study this area. So these papers have quite a bit of variability in terms of the methodologic rigor. Of course, we all are aware that there's risks of having poor methods, which can lead to, bad results or limited generalizability. So the goal of our paper overall was to try to raise standards and improve the clinical impact in this area. And then selfishly, we wanted to provide a reference for ourselves when we were doing critiques of these new incoming papers. So a lot of these topics, when I review papers now, I just say, I'll summarize it and then refer to this paper. So I bet you all also review these types of papers. Feel free to use this as a reference if that would make your life easier. So this is figure 2 in the paper. So we focused on 7 main topics, which are listed here, and they kind of span all the way from the idea formulation and study design, analysis, and then reporting of the paper. So the way that the paper is organized is it kind of goes in the order of how these topics would happen in the research process. Okay, so I'm just going to jump right in. The first topic is alignment of study goals and analysis. So it's a problem when these are not aligned. So, sometimes there's a goal of inference or hypothesis testing. In these cases, usually traditional statistical models are preferable. Whereas, a lot of these newer applications, our goal is predicting an outcome. And in those cases, you can use machine learning modeling. But something to keep in mind is, machine learning models are much more complex compared to traditional statistical methods, and they're often referred to as black boxes because of some challenges with interpretability and understanding really what's going on with the methods under the hood. And something that I see a lot is that machine learning is kind of viewed as more novel. So in terms of like grant submission or paper submission, a lot of times you're trying to make a pitch for novelty to try to get your paper or grant accepted. But if machine learning isn't really warranted, then the novelty really just doesn't make sense. Okay, so some concrete examples here. For example, if we had a clinical trial that was trying to test efficacy and safety of an intervention, in this case, we would probably use some traditional statistical inference methods. In the case where we might be like reusing trial data to develop a prediction model for something like modified Rankin scale, we could try machine learning if the data were complex or, if simpler methods really just weren't performing well. And so our overall recommendations for this topic are to use machine learning for individual level prediction, and in the case that complexity is okay. And I will add that, I think it's always better to use simpler models first. And if for some reason they fail, like if you have issues with assumptions or performance, or, in some cases, if you have like high dimensional data, for example, you might not be able to use traditional regression methods because you run out of degrees of freedom. In those cases, I think you can try machine learning or something more complex, but always simpler is better. And then use standard methods for population level inference and when simplicity is preferable. And overall here, we just really want to ensure that the goals and the aims of the study are consistent with the analysis that was applied. The next topic is kind of a little bit of a nitpicky one, but people tend to use machine learning terminology wrong a lot. And I think jargon in any field just causes confusion. And a concrete example here that I see all the time is people confusing statistical significance with variable importance. Those are not the same things. And so I think here it's just you have to be really careful about using the terms that are appropriate for the methods that you've applied. And then another just huge pet peeve of mine, which is a gray area, is like the title of a paper might be Machine Learning Prediction Model for blah, blah, blah. And then when you actually look at the methods, they say we used logistic regression, which technically some people say is a machine learning method. I would argue it's a statistical method. So again, I think sometimes people are just using the term machine learning for novelty or, to try to make it like look more interesting than it actually is. So I don't know. That's one of my pet peeves. We can discuss it later in our discussion afterward, but love to hear thoughts on that from you all. So overall, the recommendations here are that terms should be appropriately used within the context of machine learning and traditional methods. And then also just making sure that you're explaining terms or clearly defining them within the entire paper, right? So from the aims, analysis, results, interpretation, and inclusion, conclusions or discussion. Okay, so topic 3 focuses on sample size justification and the data set quality. And actually, when we were writing the paper, Wes, Andreas, and I spent, I think, the longest amount of time discussing how we wanted to put this section. So the problem here is that often in these prediction model studies, a sample size calculation or even just explaining what the sample size is and justifying it is completely omitted. And people tend to think, well, I have this small data set. I didn't find anything with my inference analysis. So I'm just going to use some machine learning and that'll be this magic fix for my messy data set that's also small and I'll just find some stuff. And we have this this phrase, hopefully you all have heard it before, garbage in, garbage out, right? So you have junk data that's really messy and small, it's going to be really hard to get anything meaningful out of it. It doesn't matter what kind of method you throw at that kind of data. It's just not going to be helpful. And this is exemplified in the literature a lot. One example is this systematic review of 69 studies of machine learning, and they were looking at attention deficit hyperactivity disorder. They found that classification accuracy was poor for data sets with small sample sizes, which to me, I'd say, well, duh, of course it's most likely going to be poor. So the recommendations here, please include a sample size calculation or justification. I think this is an emerging area. There's lots of work with these calculations. And I know Richard Riley's group has some nice R packages and software to do that. But I think there's still new methods coming out. So I think it's important to try to keep on top of those and make sure that the sample size is justified with something, either a calculation or looking at events per variables, something like that. And then also it's just really important to evaluate the data set for bias, variance, and quality issues, and then consider these strengths and weaknesses in the discussion of the paper. Okay, so topic 4 deals with the machine learning analysis pipeline. So I think, this is kind of an issue with a lot of papers, not just in machine learning, but I think sometimes there's either inappropriate or underspecified modeling pipelines. So a big one in machine learning is often parameter tuning is not discussed. Also, model validation strategies, internal validation, like using cross-validation or Monte Carlo splits. And then I think people also just confuse different types of validation, like internal versus external validation. What are those? Of course, external validation would be a separate data set, usually from like a different area or a different population. Sometimes there's temporal validation where you kind of hold out the most recent data to use as a testing set. And then I'll get into missing data. I actually have as another topic, but of course it's also part of the analysis pipeline. So a specific example of this is there was a review of 13 risk prediction models for intracranial hemorrhage in acute ischemic stroke patients. And they found that the risk of bias was high in all 13 studies because of model building considerations. So again, that's leaving out key details that would allow others to fully understand the analysis. Our recommendations here are really just include all of the details, right? Either in the main part of the paper, or a lot of times journals have word limits. So including methods in a supplement it's okay to do that as long as they're all there somewhere. We also think it's really helpful to include a figure with the analysis pipeline. And we include an example of that in the paper. And then also, it's important to try to make the code and the data publicly available whenever possible. And a lot of cases, especially in healthcare, the data has to be protected, so you can't share it. But I think it's still really important to share the code without the data, because that shows the methodologic reviewers and others exactly what you did in your analysis. So I think it really promotes transparency, and other people can replicate the study design in other data sets, even if they don't have access to yours. Okay, so missing data was a part of the analysis pipeline one, but also warrants its own discussion because this is an issue that comes up in almost every review that I do. So missing data is often ignored. It's not quantified, not mentioned, not handled properly. Of course, we have to consider missing data patterns and assumptions. A lot of people tend to do complete case analysis, which then leads to bias, or sometimes people do imputation, but I've noticed like simple imputation methods being used that are really suboptimal, for the type of study being done. So here, an example, there was this systematic review of 152 studies using machine learning. Missing data handling is awful, basically, is what they found. A third of the articles didn't even report on missing data. A third did not report on the amount of missing data, and only 10% of studies used imputation or directly addressed the missing data. Okay, so recommendations here. I mean, number one, of course, is quantify how much missing data you have. So what I always do is just include it as a column in your table one. And if there's no missing data, it's really helpful to just say there's no missing data, and then, it's very clear. Also, you have to clearly describe how missing data was handled. And specifically, when you're thinking about machine learning type stuff, there's often like cross-validation. So how was missing data handled in that? And then also in the description or the discussion at the end, how does missing data impact the bias in your results? Okay, sorry, excuse me, I have a little cold. Okay, topic 6, uncertainty measures for performance metrics. So this is really where my statistician hat shows. So measures of uncertainty are really needed to make meaningful comparisons, but a lot of machine learning methods don't automatically give you a confidence interval or a variability estimate. And so without these kind of built-in measures, people just often, put in papers whatever they get from their software that's kind of built in. And the problem is, if you don't have that variability around your performance estimates, you really can't compare different estimates because you don't know what the range of the possible values would be. So you can't make any determinations about which model might be best if you are, using a few different models. So here's a pretty astounding example here. There was a systematic review, again, of machine learning prediction models. 75% did not include precision estimates in the abstract. And again, why is that a problem? Well, then we can't really make comparisons to determine which models are best. So the recommendation here is include confidence intervals, variance, and or standard deviation around all of the key performance metrics. And then when there isn't a closed form equation for those metrics, you can use methods like cross-validation, permutation, or bootstrapping to try to get some kind of uncertainty estimates around those metrics. And then you can be able to compare them and say truly which one is better than another. Okay, last topic is in the paper discussion. A lot of papers with machine learning have like spin or hype, which is defined as intentional or unintentional reporting that inaccurately represents study methods or findings. So here's kind of some examples, but I think what I see a lot, excuse me, in papers that I review is overstating the strength of the study. So here, a systematic review, the same one I mentioned last time. 21 machine learning models were recommended to be used in practice, but 20 of these did not include external validation. So that's a huge problem, right? If you don't know how it's going to perform in other data sets, then you can't really recommend that it should be used in practice. And then this paper also found that reporting guidelines were only cited in about 8.6% of the studies, which is not ideal because then, it suggests that the methods, may be suboptimal or not communicated fully. Okay, so recommendations here, it's really important to consider bias, generalizability, interpretability, transparency, reproducibility, and the potential for clinical utility and impact. There's a couple of tools that we can recommend that can help researchers with evaluating this. The first is the Real ML Guide, which helps with understanding the limitations of machine learning research. Excuse me. The second one is the Spin PM tool, which isn't specific for machine learning, but that can help evaluate like the spin that was written in a discussion section. Okay, so overall, we also have kind of two general recommendations that really relate to all of the 7 topics that we covered. The first one is to include a statistician and a machine learning expert in the study. Now, sometimes this can be one person. Like I am a statistician and I have expertise in machine learning, but I think a lot of times we have machine learning experts who are doing the modeling and then a statistician is not included. And so the statistical aspects are really suboptimal. So definitely including someone or multiple people who have expertise in both of those areas. And then the other big one is using an appropriate paper writing checklist with machine learning specific guidance. So there's the Tripod AI one that's really great. I'm sorry. And then the other comment with this is not just using the checklist, but actually doing each item on the checklist. Like a lot of times when I review these papers, they'll have the right checklist and then they'll say like, oh, this doesn't apply to my study. This doesn't apply. But really it does. So, not just using the checklist, but actually really following every single item on them. So this is table 2 in the paper. These are a lot of extra resources to learn more about the topics that we included in our paper. And again, thank you so much for having me. And I'd love to discuss. Here's my email address if you want to contact me after this. And then this QR code takes you to my website. There's all sorts of paper links. Code repositories, etc. So yeah, let's open it up for discussion.
All right. Yeah, that was excellent. Thank you very much. And thank you again for joining us and presenting on our first meeting. Are there any questions? Oh, I see Taki already has a question. Taki?
Sorry, this is me being a Teams novice, and I was trying to give applause, but raised my hand. I just want to say this is a fantastic presentation, and a lot of the messages really resonate. So thanks.
Common mistake.
Thank you.
Okay, Mike. You're on mute. You're on mute, Mike.
Okay, I feel like Taki. I'm also a Teams novice. I'm a Zoom guy. It's showing that I don't know how to unmute myself. Thank you, Dr. Speiser, for a really amazing talk. I mean, it sounds like kind of the through line is that doing cool new things is no excuse for a lack of rigor, which seems to happen a lot. I guess I don't want to be too philosophical, but do you feel that there's something kind of fundamental about machine learning that lends itself to this kind of Wild West lack of rigor, or do you see this in new statistical methods too, where people apply like SEM or things in a, is it just something that is on the border and that it's new, or is it some fundamental philosophical difference in the way we approach machine learning?
Yeah, that's a really interesting question. Thank you. So I think my understanding of it, and this goes back to times before I was born, right? I think statisticians, are near and dear to my heart, so I don't want to knock them too much, but, they can be really judgmental with people outside of their group. And I think in the 50s and 60s, when some of these machine learning methods were being developed, they kind of poo-pooed on these ideas because they weren't mathematically driven. Mm. And so I think because of that, there was this split, and machine learning kind of became a computer science field more than a statistical field. And now I think they're merging again. But I do think because of that, machine learning moved forward, but without statisticians involved. And so there's just a lot of these very fundamental parts of doing research that are not included in these machine learning studies. But I think we're doing better now. I think, everyone is starting to play nicely together, and, especially with all these increases in AI methods, I definitely think statisticians have realized we need to play nicely with other people because it's going to move forward with or without us. And it's better if we're involved. So that's my take on it. Yeah,
that's very hopeful.
I just think, computer science and the engineering side, they just have different training than a statistician would. So,
sure, yeah.
And I'm not trying to dismiss that or anything, but it's just different worlds, I think. So coming together is the key.
Yeah, thank you. Thanks again for a really awesome talk.
Let's go, Stein. You were before Mehdi, I think.
Yeah, thank you so much, Niels. Yeah, so I'm going to join the rest in congratulating you for your great performance, Professor Speiser. I'm actually really glad that we asked you for this inaugural journal club, because I think it resonates with topics that we've been discussing a lot. I mean, this community came together in Barcelona for the first time last year, and I think many of the things that you address are the common frustrations that we also addressed. If I speak on behalf of the entire community. And so just maybe a couple of questions that I wrote down, but we won't have time to address them all. But I think indeed the fact that it's much about this methodological problems that are often not addressed, because machine learning is seen as some kind of magic tool that will give you a very nice story, and then the story is written without the rigor behind it. And in relation to that, I think there are a couple of hurdles that we should overcome. So, for example, sharing that code is I think a very interesting idea, but then there's also a problem that people just don't know how to work with GitHub, don't know how to structure their repository, making sure that they are kind of easily reproducible. and we don't have time, of course, to do these code reviews. So what is your opinion in moving forward there? Do we need separate instances that do these code reviews? Do we need to enforce certain quality standards? What do you think?
Yeah, I mean, I'm a big proponent of open science principles. Again, pretty much every review I do, you know, if it's for neurology or other journals, I recommend that people share their code. It rarely happens, right? They always write that line like, you can email the author and we'll send, yeah, I don't like it when people do that. That's another pet peeve. But yeah, I think at the very minimum, everyone should post their code. Yeah, and I mean, it's tough. Like, I don't think you have to make it super duper organized and like, I mean, I think the point is people need to be able to see what you did clearly. I think it is a little bit dangerous also, though, because especially with these AI methods, being able to take your stuff and then use it incorrectly. And I am a little nervous that, like, I've already had some of the clinical collaborators I work with, I have tried to do some of their own coding, and it's, you know, maybe 80% correct, and the rest of it is absolute junk. So I mean, it's a blessing and a curse. I think there's a lot of ways that we need to be more rigorous as a field. And I think until journals really start requiring it or funders or, you know, like there needs to be some, you know, authority figure basically mandating it, because otherwise I think, you know, some people are better about it than others, but you're right. I mean, we don't get paid extra to make this really nice GitHub repository with a README page with instructions. And I think we probably should be doing at least to some extent of that, but you know, there's no time, there's no money, there's always the next project that needs to be done.
Exactly. Yeah. Sometimes it risks for me like the extending problem of having peer review everything for free, and that also the code review gets into that there's never any time and never any money to invest in that. We only want the gold, but we don't want to invest in it.
I do have to say though, I mean, so you all are welcome to like stalk my GitHub page. It's not overly fancy. I basically just, after I'm done my analyses, I just put the code up, and that, you know, it's a little bit commented. It's not like crazy messy, but I do have to say, on the flip side, one of the benefits of that, a paper I was involved in, we had this big benchmarking analysis, you know, thousands and thousands of lines of code on GitHub, and we shared it, and a reviewer actually looked at all of it and found a typo that was sort of important. So, you know, it was great. I can't believe like the reviewer really went through all of it. And yeah, so that was awesome. Yeah, I think it's also hard as a reviewer, right? Because I already spend so much time reviewing each paper. I don't want to have to look at all the code too. Although that would be beneficial, but you know, everyone's busy, and I think already, you know, journals struggle to get reviewers. The peer review process takes way too long.
Yeah, if I can just piggyback onto what Stein was saying and what you're saying there as well, I think, unfortunately, I'm very much for open science as well, of course. I think the problem is that you have to get, even when people make their code available, you may get the reviewers that get assigned, that get invited, may have no coding experience, may have no idea anything about that, and so they don't even bother to look, or if they look at it, they don't understand what they're looking at. And there was a paper that I was interested in from last year or so, where it was an AI model, and they'd said, the authors had said, we've made the tool publicly available at this link. So I said, okay, great. I went to the link, and it was a GitHub link, but it was just stub code that did nothing.
Right.
And so then I emailed the authors and I said, hey, this was any chance that I'm curious to try your model. And of course, didn't get a response from the authors. And I felt, maybe incorrectly so, but I felt in this case that it was a little bit abusing the principle of open science, where they wrote this thing and said, no, we're making it openly available, but there's no way that someone that is making an AI model makes the mistake of not actually checking in their code and just putting in something that does nothing. So then I contacted one of the editors of the journal, and they got all of the editors involved, and they said, to the handling editor, they said, can you reach out to the authors? But then, I mean, I checked recently and the paper still stands. The link is still there so I mean, it's just I don't have a better solution, because like you said, we're already strapped for time.
I mean, I will say something that I really like about our neurology editorial board is that every paper, so the way it works is the first level of review are the clinical people, and if they basically all give their blessing to move forward, then somebody from our team reviews it for methodology. So every paper that is accepted has been reviewed for methodological considerations by a statistician or epidemiologist with expertise in that area. And honestly, I don't know why more journals don't do something like that.
Yeah, no, that's great. Mehdi, I saw you had your hand up before. Sorry, I kind of jumped in before you.
Thank you so much, Niels. That's awesome presentation, Professor. I have just one question, and then about you mentioned that the machine learning models are basically black boxes. You know, we are familiar with the methods like game theory-based method, SHAP, and LIME. I want to know what do you think about these methods, and does they help to increase explainability and interpretability of the methods? And
yeah, thank you for that question. So I am familiar with a lot of those importance metrics, and what I'll say again is, I think people from outside of statistics are working in this area, which is great. I think like a lot of these game theory came from like the econ kind of groups. So there's a statistician named Lucas Mensch who has been working in this area, and he's done some really fascinating work with variable importance metrics and random forests and other machine learning methods. He basically showed that if you just add data like columns to your data set, that you can totally change performance, importance metrics. You just add junk to your data and then the performance improves. Right? So I think the lesson there is that we have these metrics that get at importance, but like the characteristics for them are not well. So I think, it's helpful, to get a little bit less of that black box feeling. But I just think there's so many scenarios that we don't understand with them, and characteristics about like under different conditions, how will these metrics perform? And without the mathematical reasoning behind it, it's just really hard to say like, yeah, this is a good metric for variable importance, or or compare different metrics. And so I think some of these studies, like when you just add junk to your data set and improves the performance, it really makes me a little concerned. But again, I mean, a lot of people say, well, if all we care about is predicting an outcome, then, let's add a bunch of junk. Let's make the prediction better. I think it's an interesting place for all of us working at the intersection of machine learning and data science and medicine, because there is a balance. We want to be able to predict things, but we also want to understand the underlying association. So it's kind of a both scenario. It's not like one or the other. So yeah, Mehdi, I think it's a great question. I know I kind of like threw my hands up about the answer, but I think there are metrics, but we just don't fully understand all of the characteristics about them.
So it's still machine learning methods. It's still black boxes, and if we adjunct columns to it, it takes overall performance good.
Yeah.
We can't do something about that.
Yeah.
Thank you so much.
Yeah, sure.
Stein again.
Yeah, by the way, I invite everyone, of course, to raise their hand and ask a question, but I'm that much engaged that I would like to ask a second question. First, maybe following on this one, because regarding explainability, I feel that I've been a bit on the Dunning-Kruger curve, and that quite recently I was still at Mount Stupid, where I thought like, yes, please, more explainability, and not to say that that is not wanted, but it can also be a bit naive because at first I thought like, okay, we just need those metrics to better understand our models. But the more I hands-on I dig into like the explainability methods, the more clear it becomes to me that it's very hard to actually say something about what it outputs, even if it's a saliency map of, for example, indicating voxel intensity and indicating voxel performance in a brain MRI, for example, what I work with. It's sometimes very hard to exactly depict how that one voxel is actually affecting your prediction. And then you can get into a second problem, I think, is which you give a false sense of trust, which is then maybe even worse. So I'm also a bit, I really don't want to be too skeptical in that field because I'm a high proponent of XAI, but I'm actually following your reasoning there. I think it's just very important to understand mathematically what's going on. And I think for that, it makes sense, of course, that you're saying that statistical and methodological people need to be in your team.
Yeah. And, something else like we haven't even brought up in terms of explainability is what about interactions among predictors, right? I mean, I think a lot of these methods consider one variable at a time, but that's not even vaguely what's happening in these machine learning methods, right? Like one of the reasons I think, for example, like I work with random forests a lot. They are really great at these kind of higher level interactions between predictors because you could kind of think of each tree as like a giant interaction between these variables. So when you have one variable importance metric for one variable, that makes no sense because you really need to consider, 10 variables, 50 variables, how do they interact among each other? Or like you were saying, like specific voxels, and then what about like the ones that are in close proximity to the one voxel that you're looking at? And yeah, I mean, I think one of the big things that statisticians, I think, can really impact the field of machine learning and AI is dealing with correlated data. How can we leverage known correlations between predictors? How do we describe them and understand them and then associate them with our outcomes? I think, that's an area that we can really make some strides also for understanding what's going on in these models.
Thank you so much.
Back to Mehdi again.
I'm sorry, I'm asking a lot of questions today. What do you think about the recursive feature selection method and its outcome and its validity of these methods for highly correlated data sets like probably in these data sets we have in medicine and neurology? What do you think about this methods to dealing with the highly correlated variables? And you say in your presentation the simple is better, and we use these methods to get as low as variable number we can.
Yeah, I mean, so first of all, I think the question of variable selection really depends on the application. like, for example, some of the prediction modeling I've done is with electronic health record data. For that, we don't really care about reducing the number of variables because we pull it all in from the EHR anyway. So it's not like a person is like typing in every single number. But yeah, in terms of variable selection methods, I think it really is going to depend on the machine learning method being applied. And one of my papers with benchmarking actually focused on machine learning methods for random forest and comparing them. And then we did so the first paper focused on classification outcomes, and then our group did a follow-up paper for continuous outcomes that just came out last year. And what we found, even just looking at random forest, is that it's really hard to just make a blanket statement saying, oh, this method is best, right? I think it depends on like data set characteristics, like the size of the data, the number of variables. As you mentioned, you know, if you have correlated variables, I just think there's a lot of open questions. And I think it also depends like what your goal of the study is. You know, if it's purely prediction, then machine learning people would say, well, I don't really care, you know, if there's correlated predictors, this method performs the best, I'm going to go with it. So yeah, I think it's that balance of, you know, how important is the actual like biological mechanism versus just predicting an outcome. I think if you're going for the biology behind it, probably a recursive method is not ideal. But I think if your true goal is to do inference, then I don't think you should really be using machine learning anyway, in most cases. I mean, there are exceptions, of course, but that's kind of my take on it is, and you know, the other thing is you can always apply multiple methods and then compare your results, right, to see what's best. So that's kind of my take is for every data set, I at least try a few different methods and then just kind of compare. And I've rarely seen, you know, certain methods like really like do so much better than others. Like they're always within a certain standard of error from each other, for the most part.
All right, Tom, Tom, are you still there? If you're had to step away for a second, we'll go to Mike.
I can cut Tom.
Yeah.
Sorry about that. Sorry about that. There was just a disturbance in the force. I was about to ask a question, but then somebody came to the door, so I maybe can't handle the question the way I intended. Thank you for the lovely talk. My question is about you mentioning the marriage between statistical analyses and machine learning. And one of the intersections I've been thinking about is when we're predicting future outcomes probabilistically, you know, the likelihood of an event happening, you know, one of the ways we can test it is if in a new data set, the probabilities are similar. And I'm having trouble finding consensus on calibration analyses, like consensus on how to evaluate whether the probabilities are sufficiently consistent across data sets with the same predictive models. Do you have any experience with that or thoughts on it?
Yeah, so first of all, look up work by Andreas Ziegler, my co-author on this paper. He did a lot of very seminal work with calibration and what he calls, I think, probability machines. So personally, I've only really dealt with like binary data when I'm modeling, so I don't have the probability already. I typically just have the 0-1 outcomes, and then, you know, when you model something, you get a predicted probability. But yeah, I mean, I'd imagine there's metrics that, you know, are akin to like a mean square error for it, and then yeah, and my intuition would say, you know, definitely looking at some calibration curves is the best way to go. Maybe potentially looking at like Breyer scores, or, you know, there's other sorts of metrics. But yeah, definitely Andreas Ziegler is a great statistician working in that area.
Got it. Okay, thank you. And sorry that I'm running from the door, but I really appreciate you.
Yeah, thank you.
All right, Mike.
Yeah, I'm not sure how to ask this concisely. It's a bit philosophical, but I think you started it by having such a broad paper.
Okay, cool.
But what, you know, I mean, I guess the question is it such an either or thing? Like, I constantly hear that, you know, statistics is about inference and machine learning is about prediction, but that seems to me a little bit of an oversimplification, especially of unsupervised learning, where, you know, it seems to me like that there is a big potential for these types of machine learning approaches to inform more rigorous statistical models to say, you know, exactly like you said. I think that statistical approaches are wonderful for these kind of first order things where you're saying these are the important variables. But in a lot of the more interesting cases now, as you were alluding to before, it's a lot about these interactions between variables and interactions between interactions in these complex biological systems. And it seems like these unsupervised approaches have some potential because they're kind of fundamentally nonlinear and they look at things in a more gestalt way to pull apart some of that and feed it into a more traditional statistical model. So I guess I'm just wondering if you feel that there is some potential for a kind of a marriage of those approaches. Sorry if that's way too philosophical.
Think there is. Yeah, and I mean, like I mentioned earlier too, you know, in medical applications, the goal of our study might be predicting an outcome, but we're also interested in making sure that we're collecting the right predictors for modeling that, right? And we're interested in the underlying biology.
Exactly.
So
yeah.
I do think it's hard because those are kind of opposing goals, right? Because the methods that are really good for prediction are really bad for interpretation. And then I don't know, the other way, I mean, so I'm a big proponent of, you know, simpler is better, right? So although I do machine learning modeling, I've developed some methods in that area. Like people know me as the machine learning person. I never start with machine learning, right? In an analysis. I always start, let's see if we can do like a simple regression. Do we really need to do something more complex? And then we can work our way up to that if we need it. And yeah, some of the people I collaborate with, I think, get a little bit annoyed with me because of that. You know, in a grant, they want to be able to say, oh, I'm using machine learning, I'm using AI, that's so cool, it's so novel. But, you know, most of the time, their data set like just doesn't warrant that. You know, it's like 20 predictors, a very simple outcome. So yeah, I mean, I definitely think there's a lot of overlap. Also, I don't know if you're familiar with Leo Breiman's Two Cultures paper.
No.
Okay, so first of all, you got to look up that. So that's so Leo Breiman is the person who invented random forest, and he's a classically trained statistician, amazing in our field. But he was kind of on like the outside of like the statistical community because he embraced machine learning way earlier than anyone else. And you know, he's responsible for like a lot of the early decision tree methods, random forest, importance metrics. He did missing data handling. So he wrote this paper called Two Cultures, where he basically separated, you know, the traditional statisticians and then the people who were like willing to do machine learning, which he called at that point the algorithmic culture. So that paper came out, I believe, like in the early 2000s, which
like
at that time it was
2001.
like yeah, thank you. At that time it was like a wild idea. And you know, then and he died I think in like before 2010. Niels, if you remember. Anyway, so
No,
he died.
I wasn't familiar with the paper. I just looked it up while you. So I'm.
Okay.
Yeah,
So
no, I'm not.
he then, I think like a few years after that came out, he died, unfortunately. He was like, I think in his 70s maybe, but the legacy was so huge. And there was like a special issue celebrating the 20th anniversary of that paper where a lot of statisticians wrote like updated commentary on it. So, Yeah, I mean, so Mike, you asked a philosophical question. There's like 25 papers that you can read on these philosophies, but definitely start with the Leo Breiman Two Cultures, and then you can go down the rabbit hole from there.
Thank you. That sounds like
yeah.
a great suggestion. I will certainly read that.
Yeah. Yeah, it's a great paper. I have all of my students read it and talk about it. So that's a fun one. I don't know, for your journal club, you might want to do that, but yeah, unfortunately, Leo Breiman passed away, so you'll have to find a different speaker for that one.
All right. Are there any other questions? We did have this scheduled for an hour.
Yeah, I think indeed. Then maybe it's best to keep it to this then.
Yeah.
Before we go out, I would like to put the spotlight a bit on some people that made this possible. So Niels, you yourself, Smaranda and Maddie, who are all three here. Thank you very much for making this all happen. That made sure that we could have this interesting discussion. So I will leave the floor now to you, Niels, to close it. But I just wanted to point that out so that people know that there are very dedicated people working behind the scenes to make this all happen.
Yeah, no, well, thank you, Stein. But I would like to really thank you, Dr. Speiser, for joining and presenting. And this was a really, really great talk. This was really perfect. It turned out better than I think even envisioned when we were talking about kind of trying to figure out what the first paper should be that should be presented. And this was, yeah, absolutely perfect. So thank you very much for taking the time.
Yeah, thank you for having me. This was great. I love the discussion. So thank you all.
Thank you so much for taking the time.
Yeah, thank you. And I wish all of you have a nice week. Have a nice weekend. And some of you I'll see soon.
The recording, by the way, I will make it available on the website. So the event page that you just saw, I will make it available afterwards there. We'll put it on the YouTube channel of iAIMS so that everyone can also look back at it. All right.
All right. Thank you very much again.
Have a great weekend, everyone. Thank you.
Take care.
Thanks. Bye.
Bye-bye.
Bye-bye.